talked about that already? Did you guys talk about that already?
No,
No, I just knew that he was.
the guilt was already, he was wrapped with guilt.
I bet in Dr. Gagner.
Seriously? I left a perfectly good black marker that I had just gotten out of the office in here at the beginning of the day.
I saw Dr. Davis coming in. Skillet.
Dr. Pierce.
Really?
Seriously?
It's a conspiracy.
Go give them a stern talking to. They don't make them like they used to.
Hey.
Wow.
Hey.
Hey.
Welcome.
Glad you get to join us.
Glad of you to join
us. It's almost as bad as when so the question
Oh, yeah?
for our
Should
apartment
drive in the mailbox?
on our whiteboard is what actor would you want to play you? And I wanted to say Will Ferrell, except for I started to write Will Ferrell. And Andy Cotney was erasing the P. So I've been caught twice and doing something stupid.
Too big? No, I think
I'm sorry that I had in.
yeah, let's cardboard shape.
I feel no remorse.
After 6 readings, it kind of falls apart.
No, it's just regular, but
How much more can you make?
that's like mac and cheese. That's hard to do.
All right, today we're talking about semiconductors.
Can we just skip something? Britton said you really didn't want to hear about it.
Tough.
All right, semiconductors. Oh, look,
I know.
flying free. It's still in your hand.
Yeah, it's gonna put it on.
All right, two kinds of semiconductors. Two broad classes. Intrinsic semiconductors. And I bet you can guess what the other one is.
Untrinsic.
No.
Extrinsic.
Extrinsic.
Retrinsic?
Outrinsic. Anyway. Intrinsic. Which comes out first. Are essentially inherent semiconductors. That is, they're free of any kind of impurity or doping. So silicon, for example, is an intrinsic semiconductor. Just pure silicon is a semiconductor. You don't have to dope it, you don't have to put anything else in it, it just works as a semiconductor right from the beginning. Okay, so before we said the conductivity, what expression did I have for conductivity? I have defined an expression for conductivity. Anybody remember? It had the charge in it, right? Q of an electron was in there. N. What's N? The number of electrons. And what was the third piece? Mu. Or, as some of your buddies thought, muse. Muse. They thought it was muse because they kept hearing me saying muse of X, muse of Y. Because I would say muse sub X and they thought it was muse of.
Who thought that? Come on, speak up. Whoever it was.
No.
No.
No, it was Hirschberger and Ashbrook who were.
Typical football.
No. Anyway, it was kind of fun. Apparently, Serena had to come up and tell me before class so I could call him out on it. Muse. Okay, so is that it? Is that conductivity?
Yep.
No.
Yep, we're done.
Something else is missing.
L.
No, not an L. We're making stuff up. Well, you should have had.
What is mu? Whiskers.
What's that?
Oh.
Mu is the mobility of the charges. I think what I gave you before was probably whatever for the negative charges, and then the same values for the positive charges.
Okay. What you gave us, at least what I wrote down, was sigma equals Q7 and sigma total equals sigma plus sigma minus.
Okay,
So.
but you get the general idea, right? Okay. You could synthesize those two together and probably come up with this. I mean. Anyway, so it's the the number of carriers, negative or positive, the number of negative carriers times the charge of each negative or positive carrier times the mobility of each negative or positive carrier. So if we have an intrinsic semiconductor, we're going to go back to the Fermi plot. So you have a valence band here and a conduction band up here. Right? Where's the Fermi energy?
Halfway.
Halfway. Right? And then at some temperature above absolute zero, the Fermi distribution looks something like this. Right? So this region up here represents electrons that have been excited out of the valence band. This region down here represents electrons that have been excited into the conduction band. Does that make sense so far? Good. Right? The electrons and thermal energy excited these to move over there. Okay? All right. Well, we know that these are electrons. They're going to carry charge. What we have here are electron holes. There are empty spots here which should be electrons. So what that means is I can actually get conduction in the valence band as an electron that has not been excited moves into an energy of an electron that has been excited and therefore vacated. Does that make sense? What?
Kind of like the vacancies we were talking about, like with materials, if there was like a hole that would kind of, you can kind of like
Kind of like
shift
that.
through
Kind
it.
of like that. Yeah.
Okay.
Yeah. Right. So a vacancy is kind of like an electron hole. An electron hole is kind of like an electron vacancy.
Okay.
Right. So the electron hole can move by virtue of the fact that another electron fills its spot. The hole has moved in this direction. Right. And the hole has a positive charge because the electron that was taken out had a negative charge. Does that kind of make sense?
Well, it would be just like a neutral charge.
Because if that hole moves from here to here, it's the same thing as a negative charge moving from here to here. So it's I can
So
think
it's
of
more
an
like a
electron
shape.
charge moving from left to right.
Okay.
It's the same thing as a positive charge moving from right to left.
Okay.
Since the hole is the thing that's moving,
So
it's a positive charge moving from right to left. Okay? Okay. So, and we know then that the number of negative charges is equal to the number of positive charges. Right? Because the only place for those to come from is from over here. And we know that the Q of the negative charge is equal to the Q of the positive charge. Absolute value at least. So, what that means then is our conductivity is equal to N times Q times the sum of the two mobilities. Or we can write it, and the way I'm going to write it going forward is NQ times mu of the electron plus mu of the hole. So it's mu sub H, mu sub H, and mu sub E. Okay? It would be a lot more effective if I knew that they were going to watch this video later. Anyway. Okay, so as the temperature increases, what happens to N?
more, maybe bigger.
N's get bigger, right? As the temperature increases, right, the Fermi function drops down, I excite more electrons and holes. And as the temperature gets bigger, what happens to Q? Nothing, right? Q is Q, right? The elemental constant of the universe. As the temperature gets bigger, what happens to mu? Think about it. As I increase the temperature in the lattice, what do you think is going to happen to the mobility, the ability of the electrons to move through the lattice?
Increase.
And everybody spoke at once.
Increase.
Some boats are increase. Anybody else want to go with decrease? Everybody's on the increase boat.
Maybe decrease.
Make a decision.
I'm gonna say
Hold on,
50%
50%,
decrease,
50%.
50% increase, 50%, I don't know.
You won't do well at that.
All right, everybody who thinks increase,
Tell me
raise your
that
hand.
doesn't do well with that.
Everybody who thinks decrease, raise your hand.
Because second rider.
Really? The 3 women are the ones who don't vote?
Oh,
you know you have rights now. And Colin.
I didn't vote either.
The 4
man, this.
Multi-sickness.
I can't wait to watch these.
All right, you have to, now I'm going to single you out individually. Increase or decrease, Cassidy? Is a temperature increase going to increase or decrease mobility?
Increase.
Increase mobility. Increase.
No.
Decrease. No, it's decrease.
Yes!
Hot diggity!
I knew I could trust you. That's what I'm talking about.
Why?
Wait, that makes sense.
Because, exactly.
That's stupid.
As you increase the temperature, you get more lattice vibrations occurring to interfere with electrons trying to move
I thought
through.
it would just make more space because they get further.
No.
Okay.
Does that make sense to everybody now? Okay. So it's an increased temperature.
My plane laugh.
So it's an increased temperature.
I'm glad you're working on it.
N goes up. Q stays the same. Mu goes down. But it turns out mu goes down by a much smaller percentage than N goes up.
That's what I was.
Ah.
Oh, sure. That's where you
Talk
were.
about the rate of change. I thought there was a dot over it.
So as temperature goes up, conductivity goes up. Okay? So in everything else, right, in the metals, we said as temperature goes up, conductivity goes down. Because the only thing that's really at issue in a metal is the mobility part. Right? That's all it's affecting. Because we have an essentially unlimited number of conductors.
Or the number of conductors doesn't
It's fixed, right? But it's huge, right? It's huge and it doesn't change. So the mobility goes down is the only effect of increasing temperature in a conductor, in a piece of metal. But in a semiconductor, increasing temperature increases conductivity primarily because N goes up. We excite more and more charge carriers to be able to participate in the process of conduction. Okay. And so, we really need to study N's of F, or N's of H rather, N's of E. They're equal to each other, and they are proportional to E to the minus EG minus EF over KT. So they have an Arrhenius behavior, just like we had before.
Are we supposed to know what EG and EF is off the top of our heads?
What's EF?
Fermi energy.
Fermi energy. What's EG?
Gas.
Yeah.
The gap energy. Right, the gap energy is this. So this difference is
Okay.
EG.
What's K?
What's K? Boltzmann's constant. 1.38 times 10 to the minus 24. I can't remember what it is. What's Boltzmann's constant? 1.38. I can't remember the exponent.
So EG
It's 1 over. It's the inverse.
Ten
of
to the minus. If you're doing 1.38, it's 10 to the minus 1.3.
Oh, yeah, 3.3.
Okay. Anyway, what's that?
So is that just basically going to be half the E gap generally then?
Right, right. So in an intrinsic semiconductor, EF is equal to EG over 2 if we let this be 0. So the ends are going to be proportional to E to the minus EG over 2 KT. K is 1 over 6.02 times 10 to the 23rd. Right, it's the inverse of the, no, it's not exactly 1 over that. Is it 1 over that? Yes, it's 1 over that. 6 point, whatever. Yeah, that's what counts, 2.3 times 10 to the minus 23rd. Okay. So, what that means is, it's an Arrhenius behavior, and the energy, the activation energy, if you will, is half the gap energy. the Q. Remember from the Arrhenius behavior, it was like when we did the Arrhenius behavior earlier, it was a Q in the numerator of the exponential.
Hang on a second.
Q over KT, yes?
If EG equals 2EF, then EG minus R. Okay.
All right. Okay.
Good talk.
So what that means then, if we largely, we're basically going to ignore the effect on mu because it's so much smaller than the effect on n, so that we end up with conductivity as a function of temperature that's equal to some initial conductivity times e to the minus Eg over 2kT. Right? So if we plotted it on a log scale, so we plot here the natural log of the conductivity. On the horizontal scale, we plot 1 over T. I can't remember what material I did this for, but I get a line that looks like that, the slope of which is minus Eg over 2k. So, I can look at the macroscopic conductivity of a piece of silicon as a function of temperature and determine the gap energy. I can learn something about the sort of subatomic energy state of the silicon simply by measuring the conductivity. Okay, does that make sense? Okay, now the other kind, that was intrinsic. The other kind, as we mentioned before, is extrinsic.
It's not outtrinsic?
No, it is not outtrinsic. It is extrinsic. So extrinsic is superconductivity or semiconductivity that is caused by donor ions. Well, I'm not going to say donor. I'm going to say dopants. Because I've got donors and you could be donors or receptors. Okay? So there's two types of dopants. N-type dopants. Which we would use primarily negative charge carriers. Oh, that's why I should talk and not write. Charge carriers. And the other one is P-type, which, as you can imagine, use primarily positive charge carriers, so electron holes. So N-type use electrons to create the conductivity. P-type use electron holes to create them. So let's look at now. I'm not completely inconsistent in everything I've done here. Now I'm going to flip it and do my Fermi plot vertically. You know, I've done that before. Energy on the vertical axis, energy on the horizontal. Vertical, horizontal, vertical. Now we're going to do it on the vertical again. So we're going to plot energy in the vertical. So here we have the conduction band. Here we have the valence band. And then, this is for N-type. So what we've done is with an N-type semiconductor, we add a higher valence material. So let's see if I've got an example here that I'm using. I didn't specify one. Okay. If you look in your book at the table from silicon being a semiconductor in the center, we can add a P or a B. In this case, we'd be adding a P, a higher valence, further up the scale. Everybody see there? Nobody wants to bother looking at their. Okay. And if you looked at your periodic table of the elements, you would see that P is immediately in the column to the right. It is a column 5 element. Therefore, it has an additional electron and an additional proton, right? But it has the extra electron. So what I end up doing is I end up creating a. So this is EG. This is 0. And then in here I have ED, the energy of the donor electron. It's a donating electron to the process. Okay. That make sense? Because the phosphorus has an extra electron up here at the top.
What's the G stand for?
Gap.
Got the gap, right? If that's 0.
Okay. All right, so then now the interesting thing about this is the Fermi energy is right there.
So, in this case, that N proportional thing, you have to have the EG, the EN in it, because it's not. So when you're doing like the N.
Yeah, I'm trying to find a nice picture of this. So when you're doing, oh my goodness, where's the picture? Insulators. See if you've got a better picture in here. Nope, I'm not finding a better picture. Yeah, there it is. There it is. Okay. And it's not any better than mine, 467. So the Fermi energy gets pulled up. Because again, what is the Fermi energy? How do we define the Fermi energy?
That N alpha E equation.
Nope, nope, nope.
It's halfway
I'm saying, so not mathematically, how do we define it? What is the Fermi energy? What is the definition of the Fermi energy?
Isn't it like halfway between the valence bond and the next bond?
It was for this material, but what defined it as being that location? What is the characteristic of a Fermi energy?
It's the probability.
Oh, it's 0 degree Kelvin, absolute 0, 100% probability to the left, 0 to the right.
Right. And what about not 0 degrees Kelvin?
Then it's the halfway.
It's the 50%, right? The point, it's the energy at which you have a 50% probability of having an electron, right? It's 50% probability of electron at the Fermi energy. Any lower Fermi energy has a higher than 50% chance. Any energy higher than the Fermi energy has a lower than 50% chance, right? So I should actually leave this off until we talk about the temperature, and then I'll come back to it. So at 0 degrees Kelvin, at 0 Kelvin, not 0 degrees Kelvin, 0 Kelvin, where would the Fermi energy be? If it's 0 Kelvin, so think about what I've done. I have a valence band that's full. I have a conduction band that's empty. And I've put in these donor atoms that have an additional electron occupying that energy. Where is the Fermi energy at 0 Kelvin?
Halfway between 0 and
You almost have it, but not quite.
EG minus halfway between 0 and
Is
No.
it going to be closer to the valence band?
So, are there any electrons at this energy? Are there any electrons at this energy? What's the likelihood of finding an electron at this energy?
Less than
At 0 Kelvin? 100%. Right? Every one of those phosphorus atoms that I've doped it with has an electron at that energy.
halfway in between.
So, at 0 Kelvin, This is EF at 0 Kelvin, right there in the middle of those. Right? Does that make sense? So then my Fermi function kicks in. Probabilities on the right. So I end up doing this. Right? That's the same temperature above 0 Kelvin. And I start to excite some of the electrons up into that top band. But I don't deplete any from down here. Right? Does that make sense? When I do that, and actually I should have drawn this a little differently. Hold on. When I do that, when I excite them, what I've effectively done now is move my Fermi energy down to here.
So, how is that red line, how do you go along that red line with increase in temperature?
So as I increase temperature, right, all of my electrons get greater energy.
Yeah.
Right? These electrons, a portion of them anyway, have been excited, have enough energy to jump that small gap between ED and EG. Right? I only have to increase their energy a little bit to get, as opposed to over here, I had to increase, I had to have a pretty dramatic increase in energy. So I had to have a lot of thermal energy to get this, to make this jump.
Yeah.
Right? And so I ended up with this, that's why it's EG over KT. Here, I only have to make a smaller jump, so it doesn't take as much thermal energy to get these to jump up.
Why does it start up there and then go down?
Well, it starts here because initially at 0 Kelvin, this is 100% full, and that's 0. So the transition from 100% to 0 has to occur in between those two.
Why doesn't it happen? Why doesn't it go like that?
What do you mean?
It goes like this.
Because we took the graph and.
This is the probability.
We kind of
We're plotting probability
flipped the
here.
order of it.
This is 1, this is 0. Right, there's 100% probability. Initially at 0 Kelvin, the probability looks like this. 100% probability of energy up to there, 0% probability of any energy above that. Right, just like before, when this one was at 0 Kelvin, the Fermi energy was exactly between the highest energy electron that was occupied and the lowest energy, essentially hole that was not occupied.
They were plotted energy kind of on the axis.
Right, so this is
Why
what I
are we
said
plotting
earlier.
energy over here now?
I said this when I drew
No, I
the picture.
understand, but shouldn't it just rotate the whole thing? Why did you only rotate some of your axes?
It's like he.
I rotated the whole thing.
It basically
I just flipped it
rotated
like
and
this,
then
though.
flipped it.
I
So the
rotated
zero
it
and
mirror
one
image.
got
It's a
one.
mirror image about the 1, 1. About the m equals 1 line. The picture is a mirror image. Okay. You all right now? Okay. So everybody else, do you understand why the Fermi energy is halfway between ED and EG at t equals 0? Okay. Because we have the hockey. Now, as soon as I heat it up, I start exciting some of these up there. But I don't deplete any of these. Right? So my 50% line begins to move down. Right? Because the actual concentration here in the donor level drops below 50% as I get it hot enough, right? Because it's very easy, it takes very little thermal energy to get all of those electrons to jump up into the top. Once 100% of those electrons have jumped up into the top, my Fermi energy has been shifted dramatically. Right? Because there's very few of them that don't have enough energy to make it into the conduction band. Are you with me? Kind of? Okay. So what happens is as temperature goes up, the Fermi energy goes down and it approaches but never reaches EG over 2. Because if it were to reach EG over 2, in order for it to reach EG over 2, I'd have to excite so many electrons from the valence band up into the conduction band that those from the donor atoms would have to be negligible. Right? The reality is there's always going to be a few more electrons in the valence band than there are holes in the conduction band. Because those electrons will always be the number of holes excited plus the number of donor atoms that were inserted into the material. Every phosphorus has an electron that will be excited into the conduction band. And that will always mean more electrons in the conduction band than holes in the valence band. So the Fermi energy will always stay above the middle, so that we have more up here than we do down here. Does that make sense? And in this case, in the extrinsic case, since n of holes is much less than n of the electrons, right? I excite all these electrons from the donor atoms, but I don't have much going on from the hole. I mean, I don't excite much of anything from down here. So the number of holes is always much less than the number of electrons. So the conductivity is approximately equal to just the number of holes times the Q of the holes times the mobility of the holes. We don't have to worry about the electrons. I'm sorry, did that backwards. Did that backwards. The holes are small, much smaller than the electrons. So it's only the electrons that contribute to conductivity. Okay? And the energy jump that has to take place, over here it was Eg over 2. Now, the energy jump that has to take place right, or actually it was Eg minus Ef over kT, right? Now, it's Eg minus Ed over kT. Because the energy jump that I just have to get them from here to there. So now the conductivity is determined by a much smaller energy gap. So by putting a little bit of phosphorus in the material, and actually, Ne is going to be determined by the amount of phosphorus in the material. Right? That's the number of electrons that I'm going to be able to excite. So by putting some phosphorus into the material, I dramatically reduce the energy gap necessary to create conductivity. It takes much less energy to create the conductivity, though the conductivity is limited by the number of electrons, the number of phosphorus atoms I put in. So, coming back and looking at this kind of a graph again, now for the extrinsic semiconductor, over T ln sigma. So before I had this, over here this is M is equal to the same thing I had over there, minus Eg over 2K. Right, that's the intrinsic silicon. At lower temperatures, this behavior. Here, I have M is equal to minus Eg minus Ed over K. Smaller slope, because it's a smaller energy gap. So this thing right here would be the behavior across all, essentially as they get hotter and hotter, as they increase the temperature, right? This direction is increasing temperature. To the left. So as I increase temperature, I increase my conductivity, but then I get to this point, and it flattens out. What do you think happens at this point?
Melts.
Nope.
Eg equal Ed.
What's that?
Not Eg equals Ed.
No, Eg is not equal Ed.
I was really.
Eg never equals Ed.
Yeah.
What happens at that point?
Crystallize.
Yeah.
Equals ED.
EF equals ED. No. No. But phenomenologically, I'm not asking for an equation, I'm just thinking phenomenologically. What do you think happens at that point? Think about what's happening. So I increase the temperature, I'm increasing conductivity. How am I increasing? Go ahead.
Do you think, is it like it starts dipping into the BB region?
No, that doesn't happen until here. Right, because then this is when I would get on the, into the BB region, right? When I would get on the line that was associated with the exciting valence electron.
I guess, so maybe it's such that the amount.
Think about what's happening. How am I increasing conductivity as I increase temperature here?
Because you're increasing it.
I'm
Is it the
increasing.
point? Is it the point where you've used up all, or not used up, but most of them used up all the E from the phosphorus, and
Right.
as you get enough energy, you're actually taking the stuff from the original substance.
Right, this is called the saturation range. I've used up all my phosphorus, so to speak. I've excited now all of the electrons from the phosphorus. So I can no longer increase my conductivity by increasing temperature there. So the conductivity stays the same until I get to my next electron, which has to come from the valence band, so I gotta get back over here. Does that make sense? So if I dope my material with less phosphorus, this line slides down. Put more phosphorus in, the line slides up. Right? Okay? So I have a higher conductivity though, notice at every point here, I have a higher conductivity than I would in the intrinsic material. So phosphorus doped silicon has a higher conductivity at all temperatures than pure silicon.
So it's not equal, and once it comes over that line, it starts up the steeper
Yeah,
section.
right, but it's a log scale. So the difference between this dashed line and the actual line is negligible.
What I was asking was the solid line.
This
Is
one?
that equal to the line that,
This
So
solid
the
line
one
is
on-
ever so slightly above the dashed line,
okay, okay.
but so slightly as to be negligible because it's a log scale. Right, so if I'm 100, have a conductivity of 100 more, when I get up here, that 100 more is so small compared to the million, right? A million compared to a million plus 100 is essentially the same value in the high level scale. Okay. So this region is due to the dopant. This region is due to the intrinsic behavior. More dopant, I get closer, and that horizontal line moves up with or down with more or less dopant. Are we good? Okay. The other end of the spectrum, that's the N type, is going to be the P type. And essentially, it's you can imagine it's symmetrical behavior. P-type semiconductor, same kind of a plot. All right, got the valence band down here, got the conduction band up here. But now for a P-type, we're doping the silicon with boron. So we're doping it with something that has a lesser valence. And so we have E sub A, the acceptor energy. That is, the boron is lower valence, it can accept an additional electron into its shell structure. You with me? The other one could donate, the phosphorus had an extra electron to be able to donate up to the top. Here, we can accept an electron up from the valence band into the acceptor level because the boron has an open spot available for an electron in its energy level. Essentially, it has an energy level that's unoccupied. Right, it's initially unoccupied, because it's a +3, not a +4. Or a column 3 versus column 4, whatever those, what are the names of the vertical columns in the periodic table? Group 3 instead of group 4. So, where's the Fermi energy for this going to be at 0 Kelvin?
Between the bottom and the EA.
It's going to be at EA over 2. Right, it's going to be right there. Because 100% of my electrons are filled here, and I have no electrons at that level. As I increase the temperature, now I'm going to get a Fermi distribution that looks like this. Oops. So my Fermi energy is going to move to a higher level, right? That's the point where it's 50%. But now, just like I had before, but now the number of holes is going to far outweigh the number of electrons. I got a bunch of holes here, because all these electrons have been excited up into to fill the boron shell, the shell of the boron. The boron, it doesn't conduct in the boron. This is a valence band for the boron, right? So we're increasing, we're adding these electrons to the boron. But we've left behind holes and can conduct it down here now. So the number of holes far outweighs the number of electrons, and so sigma is approximately equal to just the number of holes times the Q of the holes times the mobility of the holes, and therefore is equal to some sigma naught e to the, what's the energy going to be? What's the energy I have to excite these electrons to create the hole? EA. Right, so my energy barrier, my energy gap is EA. And you get the same kind of behavior, except now the slope of the other region is going to be equal to minus EA over K. But the rest of the behavior is the same. Same idea. Good? Yes? Maybe? No? Anyway, okay, so we have, you know, I just gotta call it like I see it. So we have energy here that's EA, we have an energy here that's the difference between EG and ED, but it's always a smaller energy than the full gap. So it's always going to be easier to excite the electron up to the point where we run out of electrons or holes. Good? All right. I think next time we'll talk about semiconductor devices. And that's probably about as, we might get, we're probably not going to make it into magnetism, but we'll try it next time. It's Friday. We'll get 5 minutes back.
Yeah, you want to get out of here.
Praise!
Because I got
Praise! Wow, that's very. Did I say that?